All right, everybody, buckle up because today we are diving headfirst into the wild world of machine learning. We're tackling gradient descent. Sounds kind of scary, right? Like something you'd need a PhD to understand. But trust me, once we break it down, it'll be one of those aha moments. You guys sent us this awesome article from Geeks for Geeks, and it's basically like a crash course on gradient descent. I'm not going to lie, it had me feeling a little intimidated at first glance.
Oh, for sure, it can seem that way. But what's so cool about gradient descent is that it helps us find the absolute best solution, even when we're dealing with problems that are super complex.
Okay, so we're talking about finding the best solution, but best how? What's the ultimate goal here?
All right, so picture this. You're a hiker, right? And you're lost in this huge hilly area. Your mission is to find the lowest point, the bottom of the valley. But here's the catch. You can only see what's right around you.
Oh, okay. So it's like being stuck in a valley on a super foggy day. You can't see the big picture at all.
Exactly. And that's where gradient descent swoops in to save the day. It's like our hiker's secret weapon for navigating those hills and valleys of data, guiding them down step by step to that lowest point.
Okay, I think I'm starting to see where this analogy is going, but how does the hiker figure out which way to even go to find that lowest point?
It's like they have the special compass, but instead of pointing north, it always points downhill, showing the steepest way down.
So they're always moving downwards, basically taking the path of least resistance.
Exactly. And as they keep going down, they're getting closer and closer to their goal, that bottom of the valley.
Makes sense. Okay, so if our hiker is trying to find the lowest point, how do they know when they've actually reached it? The article mentions a cost function, which honestly sounds a little ominous.
Uh-huh. Not ominous at all.
Okay.
Think of the cost function like an altimeter for our hiker. It tells them how high up they are compared to that lowest point.
Hmm.
The lower the reading on the altimeter, the closer they are to their goal.
So in this scenario, lower is definitely better.
100%. In machine learning, this altimeter, this cost function, measures how well the model's predictions actually match the real data. Gradient descent's whole job is to adjust the model and get it to the lowest possible reading on that altimeter. Basically, it's all about getting the most accurate predictions possible.
This is where the article starts diving into some Python code to show how this actually plays out in the real world. They mention using derivatives, which, I'll be honest, took me straight back to calculus class, and not in a good way.
Haha, don't worry, we're not going to get bogged down in equations here. The important thing to remember is that derivatives help us figure out the steepest, fastest path downhill, just like our hiker's special compass.
So it's not just about going downhill, it's about finding the most efficient way to get down.
Exactly. And what's really cool is that the article shows just how simple this is in code. With just a few lines of Python, you can have a computer doing gradient descent, learning from data, and improving all the time. It's amazing to see how these concepts become actual instructions for a computer.
That is pretty mind-blowing. So the article also stresses how crucial the learning rate is. Is that basically like choosing how fast our hiker is going downhill?
You got it. The learning rate is like deciding if our hiker is going for a leisurely stroll down the hill or if they're going full speed ahead. If they go too slow, it might take forever to reach the bottom. Too fast, and they could trip, overshoot the goal, and actually end up further down the valley than they wanted to be. Finding that sweet spot, the just right pace, that's the key.
It's a delicate balance, isn't it? Not too fast, not too slow. It's about finding the perfect rhythm.
You said it. And honestly, that's one of the big challenges that data scientists and machine learning engineers face with gradient descent, finding that optimal learning rate. It can be a bit of an art form, really.
Fascinating. Now, the article also dives into the fact that there are actually different types of gradient descent. It's like choosing from different trails to get down our mountain, right? You've got your batch,
Yeah.
your stochastic, your mini batch. What's the difference?
It's all about figuring out the most efficient way to get to that lowest point, taking into account both speed and accuracy. So let's imagine our hiker is now faced with a choice. 3 different paths that all seem to lead down to the bottom of the valley. Batch gradient descent, that's like the cautious approach. Batch gradient descent, that's like taking the super cautious route, yeah.
Huh.
Like our hiker is going to meticulously survey the entire terrain, the whole mountain, before even thinking about taking a single step.
So it's all about being thorough, making absolutely sure they're on the most efficient path no matter what.
Exactly. But, and this is a big but, with tons and tons of data, this can get really slow, really fast. It's like studying a map of the entire mountain range in microscopic detail before you even start packing your backpack. On the flip side, you've got stochastic gradient descent, and that's more like our hiker just taking a quick glance around and then just going for it, choosing a direction based on, just their immediate surroundings.
Oh, so it's kind of like a go with your gut approach.
You could say that. It's definitely way faster, especially when you're dealing with these massive, massive data sets. But, and there's always a but, it can get a little chaotic. It's like setting off on a cross-country road trip without even looking at a map. You might end up taking a few detours, maybe even end up totally lost.
So where does mini-batch gradient descent fit into all of this? Is that like the middle ground?
Ding, ding, ding.
Yeah.
We have a winner. Mini batch is all about compromise. It's like our hiker checking out a small section of the map before deciding on their next move. They're not being super cautious like with batch, but they're also not rushing in blind like with stochastic. It's all about balance, my friend, finding that sweet spot between speed and accuracy. But that's actually why mini batch is usually the go-to for a lot of machine learning tasks.
This is making so much more sense now. But our trusty hiker analogy, as awesome as it is, can only take us so far, right? Real-life data is messy. It's not always a perfectly smooth, predictable descent. So what happens if our hiker stumbles onto a plateau, like one of those flat areas on a mountain, and they think they've reached the lowest point when they actually haven't? The article kind of freaked me out when it mentioned local minima.
Yeah, it's kind of like a hiker trap. And it's true, just like a plateau can fool a hiker who's tired and thinks they've made it, machine learning models can fall for this trick too. They can get comfy with a solution that seems pretty good based on the data that's right in front of them. But what they don't realize is that there might be an even better solution hiding just beyond the next hill.
Oh no. So how do we stop our hiker or our model from falling for this plateau trick?
That's where things get really, really interesting. Data scientists have come up with some pretty brilliant techniques to deal with this exact problem. One of them is called momentum, and it's basically like giving our hiker a little nudge in the right direction. So instead of just focusing on the immediate slope, they're also thinking about how fast they've been moving and in what direction.
So it's like if they've been heading downhill for a while, they're more likely to power through a small dip or a plateau, trusting their gut that the overall trend is downwards.
You got it. It's like having a little bit of faith in the journey. Even when things get tough or don't look exactly how you expected.
I love that. Now, the article also mentions something called adaptive learning rates. So if I'm understanding this right, it's like our hiker adjusting their stride based on how steep the path is?
Right on. You're getting it. Adaptive learning rates are all about letting the model take big, bold steps when the terrain is steep, and then switching to smaller, more cautious steps when things flatten out. It's all about adapting to the situation at hand, finding the most efficient way to reach the bottom, no matter what obstacles get thrown your way.
Okay, so it's not just about speed and direction. It's also about being smart and adjusting your approach as you go, because the terrain can change without warning.
100%. And that's what makes gradient descent so powerful and so widely used. It's not just some rigid one-size-fits-all algorithm. It's a flexible framework that can be tweaked and tailored to tackle a huge range of problems. It's adaptable, just like our awesome hiker.
This is making me think about how the article was pointing out that gradient descent isn't some kind of magical solution to every problem. It has its pros and cons, just like everything else in life, and just like our hiker, who probably gets tired and hungry sometimes.
For sure. I mean, on the one hand, gradient descent is really intuitive, right? It's relatively easy to wrap your head around, even if you're not a math whiz. And it's super versatile. You can use it for all sorts of things.
And I'm sensing a but coming. What are the downsides? And I'm sensing a but coming. What are the downsides?
Well, like we were talking about earlier, those local minima, those sneaky plateaus, can really trip things up. It's like our hiker throwing a party because they think they've reached the bottom when there's a whole other valley just over the next ridge.
And I imagine in the real world, that could translate to a model that seems pretty good, maybe even good enough for what you need, but it's not truly the best it could be. It's missing out on that hidden potential.
Exactly. And then there's that whole challenge of finding that perfect learning rate, that Goldilocks zone where it's not too fast and not too slow. It can take some experimenting, some tweaking to get it just right.
So let's bring it all home for our amazing listeners. Why should they care about gradient descent? How does this all connect to their lives?
Because gradient descent is the driving force behind so many of the AI tools we use every single day. Think about it. Every time you get a personalized recommendation on Spotify, unlock your phone with your face, or even see a targeted ad, and hey, sometimes those ads are spot on, there's a good chance gradient descent helped make it happen.
So it's like the unsung hero of the AI revolution, quietly working behind the scenes to optimize everything.
Perfectly said. And the beauty of gradient descent is that It can handle these massive, crazy complex data sets that are everywhere these days. Medical images, financial data, the entire internet. Gradient descent can cut through the noise and find those hidden gems, those patterns that lead to breakthroughs.
It's like having a superpower, being able to see those patterns that would normally be totally invisible.
Exactly. Just imagine, for example, using gradient descent to train a model on thousands and thousands of medical scans, trying to teach it to spot those early warning signs of a disease that even doctors might miss. It has the potential to revolutionize healthcare, leading to faster diagnoses and more effective treatments.
Hmm.
That's the power of gradient descent.
That's absolutely incredible. And here I was thinking gradient descent was some intimidating math equation that only geniuses could understand. But really, it's a pretty elegant way of solving problems, and it's already changing the world.
Absolutely. And the best part is you don't need a PhD to grasp the main idea, right?
Yeah.
Our trusty hiker analogy, that visual of the cost function as an altimeter, it makes this whole concept so much easier to understand.
Absolutely. And you know what? Even though we just barely scratched the surface here, just seeing how those equations translate into a few lines of code, it really demystifies the magic of AI, doesn't it?
I totally agree. It all comes down to understanding the core principles behind the algorithms, the why behind the how. And once you have that understanding, you start to see the possibilities everywhere.
So to our awesome listeners, if you've ever been curious about machine learning, even a little bit, we hope this deep dive has sparked something in you. If we can understand this stuff, just imagine what you can learn and explore.
It's all about asking those what-if questions, never losing that sense of wonder. Because honestly, with AI and machine learning, the possibilities really are limitless.
And on that note, we're going to wrap up this incredible deep dive into gradient descent. We've had so much fun exploring this with you.
Until next time, keep learning, keep exploring, and keep those questions coming.
We'll see you in the next episode.